you've just read a homework or test or quiz problem, and you see the word pump. You think, okay, I think I've got an idea of the fundamentals. I've got continuity equation, first law. I've been working in chapter 4 or beyond. How can I work on this pump problem, and how do the fundamentals apply, and what should I watch out for? So I do hope you're catching on the fundamentals of continuity equation, first law of thermodynamics for a steady state, steady flow open system, starting to get very repetitive to you, I hope. And so let's see how they apply to pumps. This is a very classic image of a centrifugal pump used in the process industries, lots and lots of different commercial industrial applications for transferring fluid, any kind of liquid from one place to another. Typically, in general, the objective of a pump is to increase the pressure of a liquid up to a higher level. And the purpose of doing that is to either transfer the liquid or to, let's say, get the liquid into a vessel that's at a higher pressure than the supply pressure of the pump. It's kind of common sense. What else have I shown here? Of course, this is an electric motor-driven pump. This is the casing of the pump. The liquid is going into the pump, sort of into the center of the pump, and coming out either through the top or a side. But you get the idea that it's coming in one inlet, one outlet. Notice here how I have shown the drive shaft of the pump. I've shown the arrow going out, but I've labeled W dot out as less than 0. And that's the discipline that I use when I'm labeling my sketches. I always show W dot going out, but when power is required, like a pump, it's going to be a negative number. Power is required by the pump. And I don't choose to depict a sketch by saying W in. Another thing I put on my note here is that Q dot, here's Q dot into the pump casing. Usually we consider pumps to be adiabatic processes. So I'm saying usually 0. And there's some reasons for that. But in general, you would show Q dot in on your sketch. But if you're going to consider it an adiabatic pump, in other words, where there's no heat transfer from the pump casing to the surroundings or vice versa, that would be considered an adiabatic process. Well, here's a little better cutaway view of that same centrifugal pump. And so you can see that here's the rotor of the pump, or we call it the pump impeller, where the flow is coming into the eye of the impeller. The pump impeller is spinning around, shaft driven, of course, and it's that the centrifugal forces is what drives the liquid out to the outer casing of the pump, increasing its pressure, and all that liquid is collected in the casing, and out it goes through one pipe. Another little cross-sectional view that you can see of the pump. This would be a cross-sectional view of the pump impeller, little view of the open inlet impeller here. This is another type of pump impeller, but you get the similar idea. So you see the spinning around concept, and you see how the liquid is sort of slung out from the inlet area out to the outlet area. And here's a very typical example of what you might find in the basement of a production facility or a commercial facility. It's a bank of motor-driven pumps taking a supply from various places and sending their higher pressure liquids to other places. So I've tried to pick out the second one in. Here's the inlet into the eye of the impeller, outlet through the outlet of the casing. And, so you can see various valves associated with closing off the flow, opening the flow, various support pieces of equipment, but also very clearly you see the electric motor drives on all these centrifugal pumps. Well, what's your sketch going to look like? Okay, you've got a pump homework problem or a test problem, quiz problem. What's your sketch going to look like? Here's the way I was trained to draw basically a pump, a generic pump. What I'm trying to do in my sketch, I'm drawing this circle with sort of a rectangular outlet. I'm showing the inlet state going into the eye of the pump. So do you see it? That's how I draw mine. So the inlet would conceivably go into the eye of the pump to sort of make it look like a piece of equipment. I'm showing W dot out less than 0. You can show that really anywhere on the casing of the pump you wish. I'm trying to depict it sort of like a shaft being driven, a shaft drive of the pump sort of in the third dimension going into the page. I am showing Q dot in, and I'm making a note that it's usually 0. Of course, my model, what's my thermodynamic model? Open system, steady state, steady flow. So the inflow exactly equals the outflow. This pump is not getting fatter or skinnier. It's just operating steadily, okay? Obviously one inlet and one outlet. Okay, how can the continuity equation help us? And again, this is just it's basically a screenshot of the previous videos for a turbine and a compressor. Do you see similarly that a pump, the objective of a pump is to raise the pressure of a liquid, where the purpose of a compressor is to raise the pressure of a gas, okay, or a vapor or something like that. So pumps and compressors, very similar, but I don't sketch them the same, a little different sketch, okay? But of course, the continuity equation, exactly the same. And so a couple of notes here. When you're working in the English system of units, the volumetric flow rate is usually given in terms of gallons per minute or GPM. So that is a measure of volumetric flow. A gallon is a volume, isn't it? So a GPM is a gallon per minute. And so when you're given the volumetric flow rate, you're going to be expect to immediately find the mass flow rate because that's going to come into play in your thermodynamic analysis. Another note I made is when we're pumping liquids, which is what we pump, we're usually modeling our liquids as incompressible, like tap water. We model tap water, any lake water, river water, boiler feed water. We model all of those as incompressible. And so remember that when we need to find the specific volume of an incompressible liquid, we need to know the temperature of the liquid, and then we simply go to the saturated table's temperature table and look up V sub F, the saturated liquid specific volume at the temperature of the liquid. And so that gives us V1. And remember, if we need rho 1, if we want to do it, if we want to say rho 1, A1, V1 is rho 2, A2, V2, we simply take the reciprocal of specific volume. Now, if it's incompressible, how does V1 and V2 compare? They're exactly equal. It's incompressible. Rho 1 equals rho 2 for an incompressible liquid. And so that can give you some clues in problem solving as well. And I guess I can repeat the same thing as a lot of times when you're given a number of variables, you're always trying to find that third variable. In most cases, and an awful lot of your engineering problems, you're given the volumetric flow rate of a pumped liquid. You look up the specific volume or density, and then you determine the mass flow rate. Okay, here is the tried and true screenshot of the first law of thermodynamics for an open system, steady state, steady flow with one inlet and one outlet. Now, in mine, you see that I've struck out Qn, and that's because of the usually observation. Usually, in pumping, we consider our pumping process to be adiabatic. Let's see, what else? But I have not struck out potential energy because in many situations, depending on the way you draw your control surface, this state 2 may be much, much higher than the outlet of the pump. There may be some vertical pipe that's connected to the pump, and for some reason you've been given, say, the pressure up at state 2 from at a very, very high location. And you would draw your control surface from state 1, the inlet of the pump, all the way up high to state 2. You see that in that case, your potential energy chain term would come into play if you were drawing your control surface way up high and include a very tall pipe. Kinetic energy terms, of course, the kinetic energy term change depends on the diameters of the inlet and outlet. So do you see if for a pump, if the density is the same at 1 and 2 for incompressible, and the pipe size, the pipe diameter is the same at 1 and 2, then there's no change in kinetic energy. So that's kind of a neat observation of pumping for incompressible liquids. If the pipe diameters in and out are the same, there's no change in kinetic energy. And then H2 minus H1, of course, what you're looking for here is you must know T2 and T1 in order to look up the property enthalpy as saturated liquid at the temperature of the liquid. And of course, you're always trying to find the output power, or in other words, you get a negative number, the power required to drive the pump. So that's the common engineering need when you're analyzing pumps is how much power do I need? What size electric motor do I need to select to drive this pump? Do I need 2 horsepower or do I need 20 horsepower or similar in kilowatts? So you get the idea. Of course, real quick reprise, right, is that now this third video about specific pieces of equipment and sketching, you see that I'm just copying and pasting a statement of the continuity equation, and I'm copying and pasting a statement of the first law for an open system, steady state, steady flow, 1 inlet, 1 outlet. I'm copying that over and over again. So I hope that helps. I hope that at least helps you get started when you're given problems that involve the word pump.